Good morning. So in the last class, we have seen the starting point of elementary signals. So we have seen what is a unit step signal is all about. That is u of t. What is u of t? And what was u of t minus a? That is, it is the u of t. What is u of t? U of t is nothing but all ones from t greater than or equal to 0. For t less than 0, the value is 0. So if what is u of t minus a? U of t minus a is a signal u of t delayed by a seconds. Okay, likewise we have seen what was the discrete digital step function, that is u of n. What is u of n? U of n by definition is all ones. All samples will have 1 from for n greater than or equal to 0. So at n is equal to 0 it is 1. For n is equal to 1 it is 1. So n is equal to 2 it is 1. From there on till infinity, n is equal to infinity, it is all ones. There is no value below n equal to 0. For n less than 0, the value is 0. Likewise, we have seen that is n u of n minus k, where the unit the digital step is delayed by k samples. So each n value is called a sample, and we have seen that n is an integer also. There is nothing between 1 and 2, or there is nothing between 2 and 3. Okay, so now we were discussing about r of n. R of n, that r of t, we have seen what is r of t and what is r of t minus a. Last class we were seeing r of n. So r of n is by definition that is equal to n for greater than, r of n itself is n, that is for values n greater than or equal to 0. Okay, and it is otherwise 0 for n less than 0. So for n less than 0, the value is 0. For r of n is equal to n for n greater than or equal to 0. So by definition, there was a confusion in the last class. See, where is the signal starting? See, at 0 there is no value. So obviously you can see that the sequence, one can assume that one can see that the signal starts at n is equal to 1, because there is no signal at n is equal to 0. So you can judge that the signal, one can argue that the signal starts at n is equal to 1. But by definition, this is how it starts. That is, by definition, the signal r of n starts at n is equal to 0. So at 0, n is equal to 0, the value is 0. At n is equal to 1, the value is 1. So for at n is equal to 2, the value is 2. It goes like that. So it's a perfectly right-sided sequence. For n greater than or equal to 0, there is a sequence. So for n less than 0, there is no value. Suppose we are taking k equal to 2, that is, we are delaying the signal r of n by 2 samples. That means if this was the starting point and delaying it by 2 samples, that is 1, 2. So the sequence r of n starts at 2. At 2 it is 0, at 3 it is 1, at 4 it is 2, it goes like that. Okay, so this is what, and next we'll see what is a unit parabolic function. So again, this is an analog parabolic function p of t. It is defined as t square by 2, for t greater than or equal to 0. So it's again a right-sided sequence, that is t greater than or equal to 0, the value exists, otherwise it is 0. So this is by definition, that is t square by 2. How can you ensure this one? You have to multiply the sequence t square by 2, or the signal t square by 2 by u of t. Okay, so this is the representation, and this is the mathematical function. Okay, p of t is t square by 2 multiplied by u of t. U of t takes care of this portion. Okay, then if I want to delay the parabolic function by a seconds, then p of t minus a, that is, the argument t is replaced by t minus a. This argument t is replaced by t minus a. So what happens? Instead of t, wherever t is there, we have to replace t by t minus a. So t minus a the whole square by 2. Then I told that where the sequence starts. The sequence starts at a point where the argument is equal to 0. So what is argument? Argument is t minus a. T minus a, when we equate to 0, that is equal to t is equal to a. So this is the point where the sequence starts. The sequence starts at t equal to a. So from t equal to a, that is, for t greater than or equal to a, this value exists. For t less than a, the value is 0. So how can you ensure this portion? Here it was u of t, here it is u of t minus a. So wherever t is there, you simply replace t by t minus a. So we can see the pictorial representation. That is, this is my p of t, that is t square by 2, where it exists only to the right side of 0, that is t greater than or equal to 0. Now you can see the next one, that is p of t minus a, where it is delayed by a seconds. So the starting point is where the argument is equal to 0. So what is argument? T minus a is equal to 0, that is t equal to a. So from a, the signal exists. So that is how we have written that, that is for t greater than or equal to a, this value exists. For t less than a, for t less than a, so for t less than a, there is no signal. Okay. Now we'll go to the next one, that is what is p of n, that is digital parabolic function p of n. Similarly, just replace t by n, that is n square by t, n square by 2 for n greater than or equal to 0. There it was t greater than or equal to 0, here it is n greater than or equal to 0, otherwise it is 0 for n less than 0. Okay, so this is by definition, that is p of n is n square by 2, and this portion is taken care of by multiplying it with u of n. Likewise, we can delay this digital parabolic function by k seconds, that is k samples, that is p of n minus k. Just like the previous one, replace n by n minus k. You will get n minus k the whole square by 2. So where is the starting point? The starting point of the sequence is where the argument is equated to 0. So that is n minus k equal to 0, that is n is equal to k. So the starting point is at n is equal to k. From n is equal to k, it is having this value. So this value exists for n greater than or equal to k. Otherwise it is 0. Otherwise, in the sense, for n less than k, the value is 0. So this is by definition. So p of n minus k is nothing but n minus k the whole square by 2, and this point is taken care of by this function, that is u of n minus k. So in the previous case it was multiplied by u of n, now it should be multiplied by u of n minus k, that is n is replaced by n minus k. Now we will see the pictorial representation, that is, this is my p of n, that is it exponentially rises, that is, see, at 0, that is n square by 2. We'll take an example. The function is actually n square by 2. For n is equal to 0, 0 by 0 square by 2 is 0. Then for n is equal to 1, that is 1 by 2, that is 0.5. At n is equal to 2, that is n square by 2, that is 2 square, that is 4. 4 by 2 is 2, that is here height is 2. What about this one? N is equal to 3. 3 square divided by 2. What is 3 square? 3 square is 9. 9 divided by 2 is 4.5. So it goes like that. Okay. It's totally different from the RAM function. Okay. And what is p of n minus 3? That is this sample. The starting point here it is 0. Okay. The starting point here it is 0. So where should be the starting point? The starting point is nothing but the point is n minus 3 equated to 0, that is at n is equal to 3. So this was my starting point, that is delayed by 3 samples, that is 1, 2, 3. Now here it starts. So sorry, it is delayed by 3 samples, that is 1, 2, 3. So this is the third sample here. Okay, 3 samples, 1, 2, 3. It starts here. Okay, so this is where it starts, that is at n is equal to 3 it starts, and then it goes like that. This sample is shifted by 3 samples. Okay, now a very important function called unit impulse function. Now let me first explain what is an analog, a digital analog impulse function. So it is defined as, that is, delta of t of dt integrated from minus infinity to infinity is equal to 1. That is, one thing is sure, that is, when we perform an integration, we are actually finding the area under a curve or area under a pulse. So the area under a pulse is equal to 1. Okay, so we'll see that pulse. We see that pulse. So this is the pulse which I was talking about. That is, what is the total area? Total area. So this is a type. Okay, that is, this pulse is of width delta, and it is of height 1 by delta. Okay, so what happens? That is, when delta, so what is the area of this pulse? 1 by delta multiplied by delta is nothing but 1. That is how I have written, that is here. I have written, that is integration from minus infinity to infinity delta of t dt is equal to 1. Okay, so you're considering a pulse of width delta of height 1 by delta. So the area under that pulse is 1. Okay, now there is a limiting case also. What is that limiting case? There is a bound limiting case. Suppose if this delta tends to 0, if this delta tends to 0, this is almost approaching to 0, what happens to the height? That is 1 by almost 0. 1 by almost 0 is close to infinity. That is, when time tends to 0, the height of the pulse extends to infinity. That is a limiting case. Okay, now there are some properties, very attractive properties. See, delta of t is equal to 0 for t not equal to 0. For all values of t other than 0, the value of delta of t is equal to 0. Very important point. For all values of t other than 0, the value of delta of t is 0. That is, for t is equal to 0, the value is 1. For t not equal to 0, its value is 0. Okay. Then one more thing I can tell from this one. I have shown a pulse like this. Keeping this in mind, we'll show one the definition here. That is, what is u of t? U of t, we know that. What is u of t? What is u of t? I'll show the previous one. What is u of t? Yeah, this was u of t. This was u of t. That is, from 0, it's all 1 for t greater than or equal to 0. Okay, what is u of t minus a? It is shifted by a seconds. That is, if a is replaced by delta, here it will be delta. That is, the unit step function is delayed by delta seconds. Keeping this in mind, these two signals, u of t as well as u of t minus delta, will go to the other one. So what happens if I subtract u of t if I subtract u of t minus delta from u of t, what happens? If I subtract u of t minus delta from u of t, what happens? I get a simple pulse here. That is, this whole thing, from this whole thing I subtract this much portion. So what is the remaining portion? This much will be the remaining portion. I get a pulse where the width is delta. Okay, and the height here, it is 1 here. Okay, so I hope you understand. That is, I get, when I perform the subtraction u of t minus delta, I get a simple portion like this where I take here delta, so the height is 1. Okay, so now going back to the other thing, that is, okay, so this one we have seen. Okay, so this is of width delta, and what was the height then? The height was 1 only. So what should be the height actually of the pulse? The height of the pulse should be 1 by delta. This is how it is defined. Why it is defined like this? Because the area under the curve should be equal to 1. Okay, so if it is 1, then 1 multiplied by delta is delta. It's not 1. The area is not 1. So that means we have to make this multiply by 1 by delta. So that is 1 by delta multiplied by delta. We get what? The area under the curve as 1. That is how that is nothing but the analog delta function. Okay, so that is why it is written. That is, analog delta function delta of t is nothing but this whole thing when the delta tends to 0. When delta tends to 0, what happens? When delta tends to 0, the amplitude of this one goes up to infinity. Okay, so we cannot define infinity. That is how this analog function, impulse function, is defined as an integration. Okay, now so we have seen this one. This is very important. And likewise, if I replace t by a, then what happens? Where is the value? There is only one value, that is when the argument is equal to 0. Here you can see that there is only one value when the argument t is equal to 0. Likewise, there is only one value here, that is when argument is equal to 0, that is t minus a is equal to 0, that is at t is equal to 0. That is, it is having a value 1 at t is equal to a. For all other samples, for all other values, for t not equal to a, the value is 0. Okay, so that is shown here. That is this is delta of t. It is having a value only at t is equal to 0 of height 1. And if it is delta of t minus a, it is having a value at t is equal to A. Thank you.